Welcome to the Deep Dive, the place where we turn complex source material into clarity. Today, we are deep diving into, well, the foundational core of enterprise infrastructure, Microsoft Identity Management.
Yeah, it's a big one.
We're decoding the architecture that spans from the classic on-premises data center, Active Directory Domain Services, or ADDS, right into the cloud with Microsoft Entra ID, which you probably know is the modern name for what used to be Azure AD.
And the topic couldn't be more urgent, really. We are in a hybrid world, and the traditional network perimeter, the firewall at the edge, it's functionally obsolete.
Right.
Identity is now the singular definitive control plane for, well, pretty much everything. Understanding how identity works, and maybe more importantly, how it fails, is the key to modern security strategy.
And the risk profile reflects that shift perfectly. Our sources pulled a truly shocking statistic. A recent report found that 9 out of every 10 successful cyber attacks target Active Directory.
9 out of 10, wow.
That makes ADDS a uniquely, almost universally high-value asset, holding the keys to virtually every corporate kingdom globally.
It really does. Attackers recognize that successfully compromising ADDS grants them immediate, undisputed lateral movement and privilege escalation across an entire organization, sometimes for years before detection.
Years.
Yeah, it can be that stealthy. So our deep dive today will analyze this evolution. We'll start with the deeply complex structure of ADDS, investigate the hybrid synchronization bridge Azure AD Connect, and then explore the critical zero-trust security controls like conditional access that are, well, basically mandatory for survival in 2024.
Okay, let's unpack this foundational layer then, the classic Active Directory. It's a structure built on hierarchy, almost like a massive organizational chart for digital objects. Where does the hierarchy begin?
At the top. It begins right at the top with the forest. Think of the forest as the ultimate non-negotiable security boundary. It's the highest level, encompassing all subsequent structures like trees and domains, and sharing a standard global catalog, a single definitive directory schema, and a universal configuration partition.
Okay.
If an attacker breaches the forest boundary, well, they have achieved universal compromise of all integrated systems. Game over, essentially.
Right, the keys to everything. And working our way down beneath the forest, we find the trees and domains. How do they fit in?
So the trees are collections of domains that are linked by a transitive trust hierarchy and share a contiguous namespace. Then you have the domain itself, which serves as the core administrative and security boundary. You often see organizations setting these up geographically, perhaps domain London or domain San Francisco, or maybe based on business units, to manage security policies and administer users within that specific scope.
And finally, within those domains, administrators use organizational units, or OUs. These are the structures most users probably interact with, grouping users, computers, and other objects logically, like OU finance or OU contractors.
Exactly.
OUs are absolutely crucial for applying group policy, but you mentioned this is where we hit the first of those historical architectural quirks.
Yes, the quirks are where the deep dive really begins, because they reveal limitations baked in during the 1990s that, well, they persist today.
Okay.
You would logically assume, right, that since OUs separate users into distinct administrative containers, you could reuse a username, say El Garcia, if the two accounts were in separate, distinct OUs.
That makes sense, but the sources indicate that's not true. Not for the SAM account name anyway. Why that specific constraint?
That's correct. Even if two accounts are in separate OUs, they must still have a unique SAM account name within the same domain. This lack of separate naming space within OUs is a legacy constraint. It dates back to the very origins of Windows networking. Microsoft relied on the flat namespace method of NetBIOS for backward compatibility with older systems like Windows NT 3.1 and MS-DOS LAN Manager.
NetBIOS. Wow, that's going back.
It is. The modern concept of the distinguished name, the DN, should provide unique identification regardless of the common name, but the SAM account name legacy, it just persists.
So we're forced to adhere to these ancient compatibility standards. And the consequence is that this uniqueness requirement actually violates key principles of the LDIP RFCs, the lightweight directory access protocol standards that Active Directory is supposed to be built on.
Precisely. And think about a modern, massive organization. Imagine a large government agency or maybe a major university with tens of thousands of users.
Yeah.
Common family names like Lai, Smith, or Garcia pop up constantly. Simple naming conventions just fail quickly. So IT departments are forced into complex, often confusing workarounds, adding arbitrary digits or implementing parallel unique ID systems outside of what the user naturally remembers. It's just an unnecessary operational headache imposed by history.
Right, adds friction everywhere.
Yeah.
And that leads directly to the next architectural limitation you mentioned,
Yeah.
the shadow group workaround. If OUs are so useful for grouping things, why can't we just assign permissions directly to an OU?
Yeah.
Seems logical.
It does seem logical, but this is another fundamental design decision. Organizational units, unlike groups or users, cannot be assigned as owners, trustees, or security principals.
Okay.
They just don't automatically confer access permissions. Only security groups can do that. So if an administrator needs to ensure all users in, say, OU marketing, automatically gain read access to the marketing file share, they can't point the access control list, the ACL, directly at the OU structure.
That feels like a massive oversight if the whole point of the OU is logical grouping. So the shadow group is the administrative fix for that.
It's the necessary hack, really. The standard administrative workaround is to create a custom automated process, usually a script written in PowerShell or maybe Visual Basic.
Okay.
And this script creates and maintains a corresponding user group, the shadow group, for every single OU. These scripts run on a schedule, maybe every 4 hours, updating the group membership to precisely reflect the current OU membership. And that finally enables access control based on OU structure.
Because it's a scheduled script, there's an inherent delay, right?
Yeah.
What's the security risk in that time gap?
The security risk is subtle, but it's definitely real. If a user is moved, say, from a high-privilege OU to a low-privilege OU, or perhaps they're terminated entirely, their access permissions remain active in that shadow group until the scheduled script runs and updates the membership.
I see.
So this provides a measurable window, potentially hours long, where a user or maybe an attacker controlling that user's credentials retains unauthorized access to sensitive resources. The lack of an instantaneous security update is, well, it's a significant vulnerability.
That really drives home the complexity baked into ADDS from the start. Before we move to the physical side, we absolutely have to talk about the highest value targets in any AD breach. The FSMO roles. What are they, and why are they the ultimate objective for an attacker?
Right, FSMO. It stands for Flexible Single Master Operation. These are a set of 5 absolutely critical roles that can only be held by a single domain controller or DC at any given time within their scope.
Only one.
Only one active master for each role. They ensure the integrity and consistency of the directory across the entire forest or domain.
5 roles, and they're split, right, between the forest and the domain level. Can you quickly run through what each one controls?
Absolutely. At the forest level, so applying to the entire directory, you have 2 critical roles. First is the schema master. This governs all changes to the directory's blueprint, what objects can exist and what attributes they possess. If you want to add a new property to a user object, maybe like an employee ID, you need the schema master.
Okay, controls the structure.
Exactly. And second is the domain naming master, which manages the creation and deletion of domains within the forest. Adding a new branch office domain, you need this role.
Those sound like extremely high-level strategic targets. What about the 3 roles defined at the domain level? I hear these get targeted more often.
They do, because they impact day-to-day operations more directly. First, you have the Relative Identifier Master, or RID Master. This hands out pools of unique security identifiers, SIDs, for all new objects created in that specific domain, users, groups, computers.
That's IDs, okay.
If an attacker compromises the RID offers, they could potentially exhaust the RID pool, which would be catastrophic, preventing new objects from being created. Or worse, potentially craft specific SIDs. Next, and arguably the most critical operationally, is the PDC emulator. PDC stands for Primary Domain Controller, a legacy term.
Right, from NT days.
Exactly. This role handles all password changes for the domain. It synchronizes time across the domain, which is crucial for Kerberos authentication, and it acts as the master browser in some older network scenarios. Compromising the PDC emulator often yields immediate access to sensitive credential caches and can disrupt authentication badly.
Okay, that sounds like a prime target. And the 5th role?
The 5th is the infrastructure master. This one's a bit more subtle. It manages object references between domains within the same forest. So if you rename a user in domain A, but they're a member of a group in domain B, the infrastructure master makes sure that group membership in domain B gets updated correctly with the new name.
Got it. Keeps cross-domain links consistent.
Right. So an attacker's goal, once they gain a foothold, is always to locate and compromise the domain controllers holding these 5 FSMR roles, particularly that PDC emulator, because that's basically the control key for the entire domain's immediate operations.
That clarifies the logical and, critical architecture.
Yeah.
Moving now from the logical structure to the physical. How do domain controllers and sites manage network traffic efficiently across, say, a big multinational corporation with offices everywhere?
Okay, so the physical structure is defined by sites. Sites are physical groupings, totally independent of the logical domain use structure you set up. They're typically defined by one or more IP subnets that have fast, reliable network connections between them, like a single office building or campus.
So based on network speed?
Primarily, yes. Their crucial role is managing network traffic, specifically AD replication traffic, and also directing client computers to their nearest domain controller, DC, for fast authentication and service lookups, like finding an Exchange server.
Makes sense. And those DCs now use multi-master replication, right? No more primary backup distinction like in the old days. That must have changed recovery entirely.
Correct. Big change. Every DC essentially holds a writable copy of its domain's directory partition, and the replication itself is actually a pull mechanism.
Still not push.
Yeah, replicas actively pull changes from the server where the change originally occurred, rather than passively waiting for them to be pushed out. It's generally more efficient and resilient. The whole system relies heavily on the knowledge consistency checker, or KCC.
KCC. Okay, what exactly does the KCC do? It sounds important.
It is. It's an automatic process that runs on every single DC. The KCC's job is basically optimization. It automatically calculates, manages, and optimizes the replication topology between DCs within a site and also between sites.
So it builds the map.
Exactly. It figures out the most efficient way to link DCs for replication, essentially building a highly resilient, low-latency network map for AD data. It looks for the most cost-effective path, factoring in the cost assigned to site links, which used to represent things like slow T1 or ISBN speeds, though modern networks are much faster.
Right.
It often attempts to maintain a topology, like a spanning tree or a ring, to ensure every change gets replicated everywhere with minimal delay. And crucially, if a DC goes offline unexpectedly, the KCC on the remaining DCs dynamically recalculates the topology to route replication traffic around the failure. Pretty clever, actually.
Very clever.
Yeah.
And finally, before we bridge to the cloud, the global catalog GC. We mentioned it earlier, but let's be specific. How does it allow users to search the entire forest, maybe find someone in a different domain, without the replication traffic just overwhelming the network?
The GC. It's essential for that forest-wide lookup capability and is typically hosted on several DCs marked as GC servers. A normal DC, remember, only really knows in detail about objects in its own domain.
Right.
The GC, however, provides a comprehensive searchable listing of all objects across the entire forest. The key to its efficiency and why it doesn't crush your WAN links is that it only replicates a partial attribute set, PAS, of objects from other domains.
Partial attribute set, PAS. Okay, so what's in the PAS versus what gets left out?
The PAS typically includes attributes that are necessary for locating an object, things like the user principal name, UPN, the display name, first name, last name, often email address, and maybe phone number. Basically, stuff you'd search for.
Makes sense.
Crucially, it excludes attributes that change very frequently or are large or securely sensitive. Think like the user's password hash, their full group membership list from the foreign domain, security descriptor lists, or large binary data like photos sometimes stored in AD. This minimization ensures the GC database size remains manageable and drastically limits replication traffic, while still allowing users to quickly find any object, like a user or printer, regardless of which domain in the forest they actually reside in.
Okay, that's the foundational complexity, the sort of the bedrock of on-premises ADDS. But again, as you said, very few organizations exist purely on-prem today. They live in this hybrid world, bridging this complex foundation to the cloud.
That's the reality, yeah. So we have to transition our thinking to the cloud identity paradigm, Microsoft Entra ID.
And the goal of hybrid identity seems simple on the surface. Establishing a single, common identity for users across both their on-premises resources and their cloud resources, like Office 365 or various SaaS applications they need access to. What's the main tool that facilitates that vital synchronization?
That connection is achieved primarily through Azure AD Connect. Or, well, now it's Microsoft Entra Connect, but the name Azure AD Connect is still widely used. This piece of middleware software is installed locally on premises,
Right.
and it's responsible for securely synchronizing identities, their attributes, and critically, their password information from the local ADDS environment up to the EntraID cloud tenant.
Okay, so Azure AD Connect is the bridge. Once that connection is running, organizations face three critical choices regarding how authentication actually happens when a user tries to log into a cloud service. Let's detail those three main methods available via Azure AD Connect.
Right, there are three main ways this can work. First, and often the one Microsoft recommends now, is password hash synchronization, PHS.
VHS.
In PHS, a hash of the user's local password hash, so it's a hash of a hash, is synchronized up to EntraID in the cloud. When a user authenticates to a cloud service, EntraID validates the login entirely in the cloud using that synced hash.
So no callback to on-prem.
Exactly. This is beneficial because it eliminates the real-time dependency on the local ADDS for authentication. If your on-prem DCs go down, cloud authentication keeps working. Plus, it provides immediate access to advanced cloud-native security features like leak detection or breach alerts if EntraID finds their credentials exposed on the dark web.
Got it. Okay, the second method, which does maintain a local dependency, is pass-through authentication, PTA.
Right, PTA. This involves installing one or more lightweight Azure authentication agents on premises, usually domain-joined servers.
Okay.
When a cloud user attempts to sign in, the request goes to EntraID, which then relays the validation request down to one of these on-prem agents. The agent captures the username and password and validates them directly against the on-premises ADDS, often using standard Kerberos or NTLM protocols.
So the check happens locally.
The check happens locally. It still generally allows you to use advanced cloud security features like conditional access. But the key thing is, if your on-premises agents fail or the connection to them is down, or worse, if they're compromised, cloud authentication stops working. You retain that on-prem dependency.
Okay. And the final method is federation.
Sounds more complex.
It usually is more complex to set up and manage. Federation means relying on an Active Directory Federation Services, ADFS infrastructure. ADFS is a sophisticated on-premises single sign-on service that acts as a security token provider.
Like a gatekeeper.
Sort of, yeah. It uses standards like SAML, OAuth, or OpenID Connect to issue secure tokens after validating the user against the local ADDS. Its main purpose is really to extend the reach of ADDS authentication securely to different, often external, networks or partner organizations, establishing trusted federated identity relationships. You manage the trust, ADFS issues the tokens. Okay, three options: PHS, PTA, federation. Now, we absolutely must address the risks inherent in these choices, particularly with that pass-through authentication agent. The sources highlighted a devastating exploit called the Azure Skeleton Key exploit. Sounds bad.
It is bad. Very bad. This exploit highlights the extreme danger of that persistent on-premises dependency that PTA introduces. To execute this attack, an adversary must first achieve administrative privileges on the server hosting the PTA Azure agent. That agent runs as the Azure AD Connect Authentication Agent Service.exe process.
So local admin rights on that specific server are the prerequisite.
That's the entry point. Once they have that local admin access, the attack targets a very specific mechanism within the Windows API, right?
It's nice about that.
The attacker injects malicious code to essentially intercept and modify the critical Win32 API function that the agent uses to check the user's credentials against the local directory. That function is loginuser-w.
Loginuser-w.
Specifically, the PTA agent must call this function using the do-logon type parameter set to logon32 logon network. This type of network logon is intended for services running remotely authenticating users, making it the perfect target for a pass-through authentication agent trying to validate credentials on behalf of a cloud service.
And why is targeting that specific logon32 logon network type so effective compared to, say, an interactive logon someone might do at a console?
Good question. Interactive logons, logon32, logon interactive, require the user to be, physically present or connected via something like RDP. They involve heavier resource checks and user session context. The network logon type, logon32 logon network, is designed to be much more stateless and lightweight. It's built for automated service requests, which is exactly how the PTA agent operates when validating credentials passed down from EntraID. By intercepting this specific lightweight function call, the attacker basically sits directly in the path between the cloud's authentication request and the local AD validation check.
Okay, they're in the middle. And the consequence of that interception is what makes it so high impact. You mentioned a universal skeleton key and clear text credential dumping.
Yeah, the exploit is catastrophic in two main ways. First, by manipulating the return code of the hooked login user W function, the attacker can essentially trick the agent into thinking any password is correct. They can force the agent to accept a universal, attacker-defined skeleton key password that works for all synchronized users trying to log in via that compromised agent.
Wow, one password works for everyone.
Everyone authenticated through that specific agent, yes, granting them total access at will, user by user. Second, and perhaps even more terrifying from a long-term perspective, the proof of concept exploit code published for this vulnerability shows how this manipulation allows the attacker to simply dump all the real clear text usernames and passwords that pass through the agent into a local log file, like ctempdhh.txt.
Clear text, not hashed.
Clear text. This dump happens before the actual, now bypassed, logon check is even completed by the hooked function. So within seconds of the hook being active, the attacker can harvest the actual passwords of users authenticating via PTA.
That moves the breach from potentially just a single compromised server to a total forest-wide credential loss for anyone using PTA. That sounds horrific.
Yeah.
But wait, if an attacker uses a skeleton key, wouldn't Entra ID protection or something in the cloud immediately flag that? That same password being used universally. Is the cloud somehow blind to that specific attack method?
That is the critical question, and it really illustrates why these hybrid attacks are so dangerous and difficult to detect sometimes. If the PTA exploit is successful, remember, the attack is effectively happening inside your trusted perimeter. It appears to enter ID as legitimate traffic originating from a trusted agent service running on a supposedly trusted server. EntraID protection is excellent at detecting things like impossible travel logins or credential spring attacks coming from the outside. But if the local authentication agent itself is compromised and telling EntraID, yep, this password is valid according to the local AD, then it's providing a legitimate-looking success signal, potentially even generating a valid token for the cloud based on that local but falsified check.
So detection becomes much harder.
Much harder. Detection then relies on correlating more subtle behavioral anomalies after the token is issued. Maybe the user suddenly accesses unusual resources or performs risky actions. It doesn't catch the initial logon process itself if the agent is lying. This delay gives the attacker a huge advantage.
That context is absolutely vital. Okay, now let's pivot slightly to the federation method, ADFS. This relies heavily on tokens, you said, and tokens are notoriously susceptible to replay attacks.
They absolutely are. We saw this specifically with the token replay risk vulnerability identified as CVE 2023-35348. ADFS often uses JSON Web Tokens, or JWTs, as assertion tokens. A token replay attack is conceptually simple. An attacker intercepts a valid JWT that was used during a legitimate user sign-in.
Are you sniffing network traffic?
Could be. Or malware on the endpoint, or a compromised intermediate system. They capture that token, and then they attempt to use or replay that identical token later to establish a new session for themselves, impersonating the original user. This completely bypasses any fresh authentication check or MFA requirement that might normally apply.
Okay, so the mitigation must rely on ensuring the token is truly a one-time use token, right? It can't be reused.
Exactly. The mitigation enforces the use of a unique, unpredictable identifier within the token called a nonce. Nonce is a cryptographic term, basically meaning number used once.
Never used once.
When the ADFS server issues a token now, it should contain a unique nonce value for that specific transaction. The relying party, say Office 365 or whatever application is trusting ADFS, then needs to check and ensure that it has never seen that exact nonce value before within a reasonable time window. Microsoft introduced the fix primarily by including the enforce nonce in JWT setting on the ADFS server configuration. Administrators must ensure this setting is active, which they can check using the getAddis properties PowerShell command. If the nonce validation fails because the token's nonce has been seen before, the token is rejected, effectively neutralizing the replay risk.
Makes sense. Check for uniqueness. Okay, moving from the complexities and vulnerabilities of hybrid synchronization, let's shift our focus now more fully to the cloud side, to Microsoft Entra ID itself, and the zero trust security philosophy that really defines modern access control.
Zero trust. It's become a bit of a buzzword, but the concept is the necessary mandate for this hybrid reality we're in. It's basically the recognition that the old perimeter model, the castle and moat, failed. The posture shifts fundamentally from the old trust but verify mindset to never trust, always verify. We have to operate under an assume breach mindset. That means we design our systems and policies as if attackers are already present somewhere inside the network.
So it's not about keeping them out, but limiting the damage when they're inevitably in.
Precisely. What are the three core principles that really underpin this whole architecture?
Okay, the architecture is generally built on three core pillars. First, verify explicitly. Always authenticate and authorize based on all available data points: user identity, location, device health, service or workload, data classification, detect anomalies. Don't trust based on network location alone.
Right. Implicit trust is gone.
Second, use least privilege, enforce just-in-time and just enough access, or GITJEA. Give users only the permissions they need for only as long as they need them. Plus, implement risk-based adaptive policies.
Minimize the blast radius.
And third, assume breach. This means you need to minimize the blast radius for breaches, segment access rigorously, network, user, device, application. Verify session integrity continuously and critically. Log everything so you can detect threats and improve your defenses. It transforms security from being about a static perimeter wall to a continuous lifecycle of protect, detect, and respond.
Protect, detect, respond. That cycle is key. And conditional access, CA, is the policy engine that operationalizes these principles within the Entra ID environment.
It really is the single most important security feature in the whole cloud identity stack, wouldn't you say?
I'd agree. CA uses all those identity-driven signals we just mentioned: who the user is, what role they have, what they're using as the device, healthy, compliant, where they are connecting from, location, IP range, maybe risky sign-in detected, to automate these if-then access decisions.
If-then rules.
Exactly. It's highly dynamic. If the user is identified as a global administrator and the device they're using is marked as non-compliant by Intune, then block access entirely, or maybe then enforce phishing-resistant MFA and limit their session duration. You build the logic.
Okay, let's talk about some critical security policies, the kind drawn from authoritative checklists like those from CISA or ENSTA. The first absolute mandate seems to be blocking legacy authentication protocols. We keep hearing this, but why is this still such a struggle for orgs, and why is it considered so non-negotiable?
Yeah, it remains a struggle because organizations, especially older or larger ones, often still have old scripts, maybe older multifunction printers acting as scanners, or specialized line of business applications that unfortunately rely on protocols like POP3, IMP, basic SMTP authentication, and older forms of ActiveSync.
Stuff that just works so nobody touched it.
Pretty much. It's often a painful migration project to update or replace those things, maybe involving significant cost or effort, but is absolutely non-negotiable from a security standpoint because legacy protocols do not support multi-factor authentication, period.
That's the key.
That's the killer.
Uh-oh.
If you allow legacy protocols, an attacker who steals or guesses a user's password can completely bypass your entire MFA investment and gain access to their email, potentially SharePoint data, etc. Blocking legacy authentication via conditional access is probably the single fastest way for most organizations to reduce their identity attack surface, some say by over 90%. It just closes a massive, wide-open door.
Wow, okay. Non-negotiable. And once we block those easy routes, MFA for all users is the baseline expectation, right?
Yeah.
Combining something you know password with something you have phone key or something you are biometric.
That is the absolute foundation. But we really must educate you, the listener, on the hierarchy of MFA strength, because not all MFA methods are created equal. Not even close, actually. The current security baselines strongly advocate for moving towards phishing-resistant MFA.
Phishing-resistant MFA. What does that mean in practice? What methods qualify?
That means using methods that fundamentally break the most common phishing attacks, where the user is tricked into entering their credentials and maybe even an OTP code on a fake website. Phishing-resistant methods include FIO2 security keys like YubiKeys, Windows Hello for Business using biometric, face fingerprint, or PIN methods tied to the device's TPM chip, or PIV smart cards that leverage certificate-based authentication.
How do they resist phishing?
They typically use cryptographic challenge response mechanisms tied to the specific website origin and the physical device. The secret material never leaves the secure hardware, the key or the TPM. You can't trick a user into typing their FIDO2 private key onto a fake website because they don't know it, and the key itself won't talk to the wrong site.
Got it. So where do the really common methods like the Microsoft Authenticator app, push notifications, or OTP codes fit into this hierarchy?
The Microsoft Authenticator app, when using push notifications with number matching, or the phone sign-in method where you tap a number on your phone, is considered stronger MFA. It's definitely far, far better than just a password and much better than SMS.
Okay.
But it's not technically phishing resistant in the same way FIDO2 is, because a very sophisticated attacker could potentially still try to trick a user into approving a push notification they didn't initiate, though number matching helps a lot here. OTP codes from apps are also stronger, but still potentially phishable if someone types the code into a fake site fast enough.
And the weakest forms.
The weakest MFA, which many organizations and security bodies like CISA are now instructing should be disabled entirely if possible, is SMS text messages and voice calls delivering OTP codes. These are highly susceptible to SIM swapping attacks, social engineering the phone company, or even SMS interception malware. They are considered weak links that should be phased out as quickly as possible in favor of app-based or, ideally, phishing-resistant methods.
Right, disable SMS voice MFA.
Yeah.
That's a clear takeaway. Now, beyond the credentials themselves, the management philosophy around passwords has undergone this radical shift. The guidance now is that user passwords shall no longer expire. That goes against decades of IT tradition. Why the change?
Yeah, this throws a lot of people, but it aligns directly with modern NIST guidelines and research. The old practice of forced password expiration, making users change passwords every 30, 60, or 90 days, actually led to predictable, weaker password behavior. Users, forced to change constantly, would just make small, predictable modifications, like password spring 24, then password summer 24, then password fall 24, or they'd write them down. It provided negligible real security benefit because the passwords weren't necessarily stronger, just different but predictable, while significantly increasing operational cost and user frustration.
Okay.
The focus now is on blocking bad passwords entirely using features like Entra ID password protection, which checks against global lists of known breached passwords and allows custom banned word lists, and then relying heavily on MFA and proactive threat detection, like Entra ID protection detecting a leak, rather than forcing constant, often ineffective changes. Strong initial password plus MFA plus detection beats forced rotation.
Makes sense when you put it that way. Okay, now let's get to session management. Controlling the duration of an active login session seems critical for mitigating the risk after someone is authenticated, especially if their session token gets stolen somehow.
Absolutely critical. If an attacker manages to hijack an active session cookie or token, the utility of that stolen token needs to be severely time-limited. Policy guidance, like from CISA, mandates that the sign-in frequency shall be configured to 12 hours maximum using conditional access.
So re-authenticate at least twice a day?
Essentially, yes. It forces users to reprove their identity periodically, even if they've kept their browser open. Furthermore, persistent browser sessions shall not be persistent. That means when the user closes the browser window, the session token should be invalidated by default. This prevents an attacker from finding a stolen token on a compromised machine hours or days later and just resuming the session without re-authenticating. Close the browser, session dies.
Got it. Limit the window. And let's address external collaboration, business-to-business, or B2B guest access. This is obviously essential for modern work, but it also feels like a massive potential risk vector if not managed tightly. How does Zero Trust policies recommend locking this down?
Securing B2B collaboration requires rigorous entitlement management and clear policies. First, you must restrict who has the ability to invite external guest users into your tenant. Ideally, this capability shouldn't be open to everyone. Only users assigned the specific guest inviter role in Entra ID should be allowed to send out those B2B invitations.
Limit the inviters.
Exactly. Second, and maybe even more importantly, organizations should maintain explicit allow lists or perhaps deny lists to control which external domains invitations can actually be sent to. You should restrict invitations to only specific, known, and authorized external partner domains, preventing accidental or malicious invitations being sent to random personal email addresses or competitor domains.
So control who invites and where they can invite from.
Precisely. It closes down a common vector for introducing untrusted identities.
Okay, let's try to illustrate conditional access with a powerful real-world scenario the sources mentioned, focusing on data leakage protection, the limited access feature in SharePoint and Exchange Online. How does that work?
This is a great example of the nuance CA offers beyond just a simple block or allow decision. Imagine you have devices identified as non-compliant by Intune. Maybe they are personal mobile phones, BYOD, or unmanaged computers that haven't met the organization's security standards. Perhaps they lack required antivirus, aren't encrypted, or are jailbroken.
Okay, risky devices.
For these devices, you can apply specific conditional access policies targeting services like SharePoint Online OneDrive for Business, or Exchange Online that grant what's called limited access. What this means is the user, connecting from that non-compliant device, can still view documents or emails directly in the web browser.
So they can still work, sort of.
They can still read, yes. But the policy actively prevents them from executing high-risk actions like downloading the file locally onto the unmanaged device, printing the document, or even copying content from the document to the clipboard. This significantly mitigates the risk of sensitive corporate data leaking onto an unmanaged, potentially insecure device while still allowing some level of productivity. It's granular control.
That's a really dynamic and practical approach. But even the best preventative controls need active threat intelligence layered on top. This brings us to Entra ID protection, which you mentioned relies heavily on machine learning. How does that work?
Right. Entra ID protection is essentially the detection and automated response engine for identity threats within the Microsoft Cloud. It continuously analyzes user behavior, sign-in patterns, and connection metadata using sophisticated machine learning algorithms trained on, well, trillions of signals Microsoft sees daily.
Trillions.
Trillions, yeah. It's watching for anomalies, things like a user signing in from a geographically impossible location compared to their last login, impossible travel, or attempting access from an unfamiliar IP address known to be associated with malware or botnets, or perhaps using credentials that have recently been identified as compromised in a known public data breach.
Okay, it spots the weird stuff.
No.
And then it translates those findings into a quantifiable risk level.
Precisely. For each sign-in attempt, and also sometimes for the user account overall based on offline analysis, it calculates a risk level typically categorized as low, medium, or high. This score indicates the statistical likelihood that the connection or the account compromise was not initiated by the legitimate user. Low risk might just be logged for information, but medium or high risk can and should trigger automated responses.
And what kind of automated responses can be triggered based on that risk score?
Those automated responses are actions enforced by conditional access policies that are explicitly configured to use the sign-in risk or user risk as a condition. For example, you might create a CA policy that says if sign-in risk is detected as medium or high, then automatically require the user to perform MFA, even if they normally wouldn't need it for that connection.
Steps up the security.
Exactly. Or, for sign-ins detected as high risk, maybe the policy immediately requires the user to perform a self-service password reset, SSPR, before granting any access at all, instantly remediating the potential credential compromise. This is the automate respond pillar of zero trust in action, using risk detection to drive policy enforcement.
Very powerful. Okay, let's shift focus now to arguably the highest value targets within any environment.
Yeah.
The privileged accounts. The keys to the kingdom for both the forest and the cloud tenant. How do we protect those?
Yeah, protecting privileged accounts, your domain admins, enterprise admins, global admins, etc., is the absolute ultimate security challenge. They are relentlessly targeted. The modern mandate, driven largely by concerns over those hybrid synchronization risks we discussed, states that highly privileged user accounts, especially roles like global administrators and EntraID, shall be cloud only.
Cloud only. And what's the core strategic reason for that strict cloud only requirement? Why not sync them?
The primary reason is isolation and containment. Think about it. If your on-premises ADDS environment is successfully compromised by ransomware or some sophisticated attacker achieves domain admin rights locally, you absolutely do not want that compromise to automatically synchronize up via Azure AD Connect and grant the attacker equivalent control over your entire cloud tenant.
Breaks the chain of compromise.
Exactly. By making those highest tier privilege accounts cloud only, meaning they exist only in EntraID and are not sourced from or synchronized with the on-premises directory, you establish a firm line of defense. You ensure that even a full ADDS forest compromise doesn't automatically result in a complete cloud tenant takeover. It contains the blast radius.
Makes perfect sense. And once we've isolated those privileged accounts, we then need to enforce just-in-time JIT access using tools like Privileged Identity Management, PIM, right?
JIT is absolutely essential for enforcing that principle of least privilege we talked about. The rules should be: permanent, standing, active role assignments shall not be allowed for highly privileged roles like global admin. Nobody should be a global admin 237.
So how does PIM work then?
Instead of permanent assignment, access becomes temporary and eligibility-based. The user is made eligible for the role, but it's not active. To actually use the privileges, they must actively request elevation into the role through the PIM system. This request often requires justification, maybe multi-factor authentication again, potentially even approval from another person.
Okay.
And once approved, the access is granted only for a strictly limited time period, often configurable down to just an hour or two. After that time expires, their privileges are automatically revoked. This dramatically reduces the window of opportunity for an attacker if that privileged account happens to be compromised while it's active. The privilege evaporates quickly.
Limits exposure significantly. Now, speaking of on-premises services that might still interact with cloud data, we briefly touched on Active Directory Rights Management Services, ADRMS, earlier. How does this older technology fit into the modern protection schema, especially compared to cloud solutions?
Right. ADRMS is the on-premises server software for information rights management, or IRM, while Microsoft Information Protection, MIP, now part of Purview, is the modern, integrated, cloud-based solution for data classification and protection. Many organizations still have legacy deployments of ADRMS or use it for specific
What's
scenarios.
its core function?
Its function remains crucial where it's used. It applies persistent protection directly to documents and emails using encryption and selective denial of rights. It controls who can perform what actions on a protected file like corporate emails, sensitive Word documents, PDFs. It can restrict operations like viewing, editing, copying content, saving locally, or printing the document even after that file leaves the corporate network perimeter, for example, if it's emailed externally.
Is the protection travels with the file?
Exactly. The permissions are embedded within the file itself, enforced by RMS-aware applications like Microsoft Office. Administrators can define specific rights policy templates like company confidential read-only or allow users to define custom protection. It's a form of data-centric security.
Okay, useful context. Now let's circle all the way back to that initial shock statistic. 9 out of 10 attacks target AD. If the worst happens, if a ransomware attack successfully compromises the core Active Directory forest, what exactly is the operational nightmare facing an organization during recovery? You mentioned recovery can take days or even weeks. Why so long?
It is truly catastrophic because the complexity of properly recovering Active Directory from a major compromise, especially ransomware that might have altered AD objects or spread laterally via AD, is almost unparalleled in enterprise IT recovery scenarios.
Yeah.
The standard documented recovery process involves nearly 40 high-level, discrete steps. It's incredibly intricate.
40 steps, wow.
Yeah. You cannot simply restore a system state backup of a single domain controller and call it a day, especially if multiple DCs were hit or if the ransomware had time to replicate malicious changes. You must first ensure any compromised DCs are completely isolated from the network. Then you typically need to perform a clean OS installation on recovery hardware. And then you have to decide whether to conduct a non-authoritative restore, or, much more complexly and often necessary after malware, an authoritative restore of AD objects.
Okay, what's the crucial difference between non-authoritative and authoritative restore, and why is authoritative such a nightmare?
A non-authoritative restore is simpler. You restore a DC from backup, but then you let it essentially rebuild its directory data by pulling the latest information from other surviving, hopefully clean DCs in the domain via normal replication. It catches up. An authoritative restore is needed if you need to roll back specific changes that were maliciously made and already replicated across the forest, for example, restoring user accounts or OUS that were deleted by the ransomware, or fixing group memberships the malware altered. To do an authoritative restore, you have to restore a DC from a backup taken before the malicious changes, keep it isolated, use specific command line tools like ndsutil to mark the specific objects or subtrees you need to recover as authoritative.
Tagging them as the correct version.
Exactly. You're essentially increasing their internal version number so that when this DC is reconnected, its version of those objects is considered the final truth and will replicate out to all other DCs, overriding the bad data that might exist there. It's complex, error-prone, and has to be done very carefully to avoid further corrupting the directory.
So just relying on generic tools like the built-in Windows Server backup or maybe a standard VM snapshot, that's not going to cut it for this kind of forced recovery.
Absolutely not. They are generally insufficient because they lack the specific AD-aware intelligence and orchestration capabilities needed to manage the complex, forest-wide restoration process required to guarantee a clean, consistent, and ransomware-free state across all DCs. You need specialized AD disaster recovery solutions that understand AD replication topology, can handle issues like replication quarantine to prevent reinfection, manage tombstone lifetime synchronization issues during restore, and orchestrate the specific sequence required to safely restore FSMO roles and ensure the entire forest becomes coherent and uncorrupted after the restore.
And that sheer complexity, coupled with the need to carefully sequence these steps and replicate potentially large amounts of data across geographically dispersed DCs, that's what leads to recovery times stretching into days or even weeks.
Exactly. For a large, complex, multi-domain, multi-site forest, the process of carefully cleaning, restoring, validating, and ensuring the consistency of Active Directory can easily take days or weeks, during which time the entire organization is likely crippled, no logins, no access to resources. That massive business disruption cost is the ultimate argument for why proactive zero-trust security and robust identity protection MFA everywhere, PM for admins, conditional access policies, rapid detection, and yes, specialized ADDR planning are absolutely essential preventive measures. Prevention is vastly cheaper than this kind of recovery.
We've covered a huge amount of ground today. We've journeyed from the deeply complex, sometimes quirky legacy constraints of on-premises Active Directory domain services with its net BIOS-related naming issues, the shadow group security gaps, and those critical FSMO role targets, all the way to the dynamic, identity-centric security controls and philosophy embodied in Microsoft Entra ID and Zero Trust.
Yeah, it's quite the evolution. The core strategic takeaway for you listening has to be that security has definitively moved inward, away from the perimeter. We must reinforce credentials using phishing-resistant MFA wherever possible. We have to ruthlessly reduce the identity attack surface by blocking legacy protocols and enforcing just-in-time access via PM for all privileged accounts. And critically, we need to automate the detection and response to identity threats using tools like Entra ID protection, feeding into conditional access policies.
Identity truly is the final, non-negotiable perimeter in this new age of assumed breach. Everything hinges on it.
Absolutely. And that leads me to a necessary, maybe provocative final thought for you, the learner, to ponder. We spent some time discussing how attackers exploit critical hybrid infrastructures, specifically highlighting the skeleton key exploit, targeting those on-premises pass-through authentication agents to achieve widespread credential loss and maintain persistence.
Right, bypassing local checks.
And we also know that modern defense relies heavily on correlating intelligence across the vast expanse of the intelligent cloud. You hear Microsoft talk about their security graph collecting over 6.5 trillion signals per day from billions of sources worldwide to detect these emerging threats.
6.5 trillion a day is staggering.
It is. So here's the question. If sophisticated attackers are already leveraging advanced methods, maybe even their own forms of data science, machine learning, perhaps rudimentary AI, to rapidly learn from their failed attempts, to blend in with normal network traffic, and to successfully masquerade their malicious activity as background noise.
How does that correlation engine possibly keep up effectively?
Precisely. How should organizations, and indeed vendors like Microsoft, approach the monumental task of monitoring and correlating those trillions of signals with sufficient speed and accuracy? How do we ensure that our automated responses, like conditional access policies requiring MFA or blocking access based on detected risk, are not only rapid enough to defeat these next-generation, potentially AI-driven attacks, but also accurate enough that they don't generate an overwhelming flood of false positives that grind legitimate business operations to a halt?
Balancing speed, accuracy, and business enablement at massive scale.
Exactly. The answer likely lies not just in collecting more signals, but in the sophistication and adaptability of the intelligence used to sift through them, understand context, and make near-instantaneous decisions. It's an ongoing arms race.
A question that fundamentally puts the scale and challenge of modern cyber warfare into sharp perspective. That's all the time we have for this deep dive. Thank you for joining us.
Stay well informed, keep learning, and stay secure out there.